Okay, please let me know if you could not hear my voice clearly. Okay. Okay. So for today class, okay, we learn on the preloading, okay, and also usually for the preloading there will be a combinations on the use of vertical drains, okay, to accelerate the process of the consolidations. Okay. And we could not use the vertical drain alone, okay, because the vertical drain uh, is to provide what we call as a additional drainage, okay, to to allow for the excess pore water pressure dissipate from the soil or from the ground, soft ground area. We can use the preloading, okay, only without having the vertical drain. However, let's say when we apply the preloading, okay, the time given for the construction to be completed uh, is still not enough. Okay? So then they need to use the vertical drain. Okay, so let's say if the application of the vertical drain and preloading also still not enough, okay, in terms of time, so then they need to apply what we call as a surcharge. Okay? Because the surcharge is not a permanent structure. Okay? So after it reaches the certain what we call as height, okay, of the structure, okay, so then they may remove, okay, the additional loads that called as a surcharge. Okay. All right. Okay. So the principle of the preloading, okay, suitability and applications, advantages, limitations, design considerations, and design procedure, okay, will be discussed today. Okay. So I also include several examples to explain on the preloading, vertical drain, okay, uh, preloading plus vertical drain, okay, and stage of constructions. Okay. So for the stage of constructions, okay, I will share with you one example, okay, a little bit complicated in terms of to understand what we call as the times, okay, the stage constructions. Okay. So as we have discussed before, okay, so there is a lot of what we call as surface loading, okay, that we use. Okay, for example, the conventional plate or roller compactions has been used for many years, and the idea is to densify soil to a shallow depth by repeating passing of a vibratory plate or a roller on a relatively thin leaf. Okay. So that is for the surface or shallow compaction efforts. Okay. So there is a new technology that has been developed in recent years. They call it intelligent compactions, and this technology has evolved in past year to research and implementations. In addition to providing the same compaction capacity as conventional compaction, So intelligent compaction includes sensor which provide feedback on the location, stiffness, and machine driving on soil on a color code map. Okay, so with this map, an engineer operator can identify area that require more or less compaction to create a uniform foundation scheme. So that is the use of the technology, okay, for the compaction approach. Then we also have discussed on the deep dynamic compactions, okay, extend the depth of the soil irrigation to greater depth by applying high energy impact through repeated dropping of a large and heavy weight on ground surface. Okay. So we have rapid impact compactions as an intermediate compaction technology from shallow to deep compaction, and it rapidly apply impact on the ground surface using a hydraulic hammer. So then we also have a vibro compaction where the idea is to densify concentrated soil by driving a vibrating probe into the ground to apply lateral vibratory force which rearrange particles into a dense state. Okay. So that is what has been discussed before. Okay, is that by the use of mechanical methods, okay, so either we can compact or densify at the shallow range, okay, and with the use of the technique vibration, okay, so then we can also densify at several depth range. Okay. However, for the concept of the preloading, okay, a little bit different, okay, where the process of the compactions or compressions, okay, is happen by we reduce what we call as the void ratio, okay, because we understand that in soil, okay, there is a three-phase material or three-phase material inside the soil, okay, where we have a solid, air, and also water. Okay. So then when we deal with saturated cohesive soil, okay, so the solution to densify this saturated cohesive soil, okay, by reducing the voids, okay, or compress the voids, whereby we reduce the air inside the voids, okay, and also expel out the water inside the voids. Okay? So in that case, we reduce the void ratio in the soil compositions. Okay. So that is the concept of the pre-loading. Okay. Okay, preloading is one of the traditionally but still commonly used ground improvement method in practice. Okay? So especially when we deal with soft soil conditions, okay? So the preloading is considered as an effective method. Okay. Okay. So this is the concept of the preloading. Okay. Temporary loading applied at the construction site with or without vertical drains and other consortium technique applied on or inside the ground to improve the subsoil characteristics. Okay. So before we construct for any building, okay, so we need to strengthen up this weak and compressible soil, okay. to certain desired strength, okay, or reduce what we call as the compressibility of the weak soil. Okay. So the idea of the preloading, okay, is to reduce board ratio, therefore reducing compressibility of soil through consolidation by applying load on the ground surface for a certain time period and then removing it for construction of a permanent structure. Okay. Usually the apply loads that we apply on the weak soil should be greater than the load from the permanent material or from permanent structure. Okay. So preloading may be defined as temporary loading applied at the construction site with or without drain, vertical drain, and other techniques applied on or inside the ground to improve the subsoil characteristics against precompression. Okay. So once we have achieved desired heights, okay, so then we can remove the temporary surcharge field, then start to construct for the proposed building. Okay. Okay, this is the concept of the preloading. Okay. So during the preloading, settlement develop with loading and time. Okay. So we look on this. Let me sequence. So this is the load. What this is settlement. Okay. So during the process of preloading, okay, so we found that the settlement, okay, will be increased. Okay. So then we continue the loading process. Okay. And the aim is to achieve at least 80% of consolidations. Okay. So how to determine the 80%? Okay, we need to use the degree of consolidation equations and also based on the time factor equations. Okay. So then we remove the preloading. Okay. So the soil start to rebound. Okay. Let's say if we continue the preloading process, okay, so there will be a continuous settlements. Okay? So it means that at this stage, okay, with the aim to achieve 80% of consolidations, okay, if you let the preloading on the soil, okay, so then if we continue until it reach at least 90% of consolidations. Okay. So once we remove the preloading, okay, it starts to rebound. Okay. And then we apply structure, or we start to we start to construct for a building, okay, on the top of our soil. Okay. So then, due to the structure load is less than the previous loading applied on the soil, okay, so then the process of settlement still occur, but it doesn't reach, okay, what we call as the maximum consolidations, okay. It only lay, okay, a little bit above the 80% of consolidations curve. Okay. So due to the structure is permanent, okay, then the process of consolidation will stop or reach, okay. However, it doesn't reach to the maximum of the from the if we apply on the continuous settlements. Okay. So the construction of the permanent structure in this new settlement due to the increase of the new loads. Okay. However, the induced settlement by the structure after periodic is expected to be much smaller than that without the preloading. Okay. So means that we need to know what is the structure loads, okay? And at the same time, the preloading load should be greater than the structure loads. Okay? Okay. Okay, for soft soil, the construction may take a longer time to complete due to their low probability. So if the time for preloading construction of the structure exceed the available times, okay, so vertical drain can be installed to shorten drainage distance, thus accelerating the rate of consolidation and reducing the time for soil consolidation and settlements. Okay, so means that we need to know what how long the process will be completed. Okay, if once we have carried out for the preloading, okay, then the maximum loads that we apply on the preloading, okay, also should not exceed the bearing capacity of the soil. Okay, so if it exceeds the bearing capacity of the soil, okay, there will be a foundations problems. Okay, so later on, okay, I will show with you. I will show to you, okay, how to identify the bearing capacity. Okay, of the soil. Okay? So then we know what is the maximum load that we can apply, okay, at certain stage of the construction of the pre-loading. Okay. So let's say if the time of the construction is not allowed for a longer time, okay? So then the idea of the use of the vertical drain, okay, is the another alternative, okay, can accelerate the process of consolidations. Okay. So as you can see in the figure, preloading can be done by placing fill on the site. Okay. Then this requires the use of significant fill. Okay. So then transportation placement of fill take time and cost money. sometimes feed placement induce failure and large movement. Okay. So later on, there will be another concepts, okay, where the use of the vacuum preloading, okay, because it doesn't involve lot of loads or field, okay, during the construction. It only use what we call as a vacuum methods, okay, to reduce the atmosphere pressure. From there, they have a negative atmospheric pressure. So then it can help to accelerate the process of consolidation with the use of the vacuum preloading methods. Okay. So then to overcome the issue of the transportations and placement of the field, so the concept of vacuum preloading has been used. So the next is the brief explanations on the vacuum preloading. Okay. So a vacuum preloading system typically includes a vacuum pump, okay, impervious membrane liner, sand drainage liner, sand drainage layer, water collection pipe. Okay. Definitely we need to use the vertical drains and a trench and clear revetment to see the boundary and prevent leak. Okay, because they use a pump, so they need to make sure that there are no leak, okay, uh, on the constructions of the vacuum preloading methods. Okay. So permanent structure will be constructed after preloading and are expected to have small settlement. So soft clay typically have low shear strength, which may limit the magnitude of the applied loads. Okay, under such condition, stage construction is needed to increase the allowable load by stages. Okay. So because first we need to know what is the desired heights, okay, to build for any geotechnical structure, for example, embankment. Okay. So, however, we cannot construct the preloading, okay, in a one time, okay, at the one time. Okay. So what should we do? We need to construct it in a stage constructions. Okay. Because as I mentioned before, okay, uh, we need to calculate for the bearing capacity of the soil, and it should not exceed the capacity of the soil. Okay. Therefore, we need to apply for the stage constructions. Okay. Okay, different for the vacuum preloading, okay, different from the field preloading. So vacuum preloading utilizes atmospheric pressure on an airtight system installed in the field by applying vacuum inside the systems. Okay. So as we know, the natural atmospheric pressure, okay, is 100 kPa. Okay. So then we may decrease the atmospheric pressure by using the vacuum. Okay. From there, it can uh, what we call as it can one we use the atmospheric pressure, so there will be an suction activity occur. Okay. So this will suck the water, okay, going out from the uh, from the soft soil area. Okay. So the vacuum preloading system typically includes a vacuum pump, impervious membrane liner, sand drainage layer, water collection pipe, vertical drain, and a trench and a clear embankment to seal the boundary and prevent leak. Okay. Okay, when the vacuum pressure is not sufficient, because the maximum, as I know, okay, it can go up to negative 80 kPa. Okay, so if the system doesn't work with the negative 80 kPa, so then need to fill an additional loads whereby to increase the preloading pressure. Okay. Therefore, the applied loads in preloading can be fill, vacuum pressure, or combination of fill and vacuum pressure. Okay, vacuum pressure will be removed after the completion of preloading, while fill may be removed or remain as a part of the structure. Permanent structure will be constructed after preloading and expected to have small settlement. Soft clay typically have low shear strength, which might limit the magnitude of the applied loads. Under such conditions, construction is needed to increase the allowable load by stages. Okay. So that is the use of the vacuum preloading. Okay. So it has an advantage that we may not transport a new or a filling material, okay, at the field. Okay, so we just use the vacuum methods, okay, to to accelerate the process of construction by dissipate the excess pore water pressure from the weak soils. Okay, now we look on the suitability of the preloading methods. Okay. So preloading is often cost effective to improve saturated, okay, low strength, and high compressible clay and seal. Okay. When the time is not a major concern. Okay. So means that if there are no limitation of time, so then the preloading itself is suitable to be used. Okay. So, for example, okay, when we want to construct for a bund, okay, to mitigate the flood problems, okay. So the bund, okay, there will be no structure on the top of the bund, okay, or any uh, continuous loading like a traffic, okay, on the top of the bund. So then we just let the process of the preloading to continue. Okay? Then there will be no times issue. So vertical drain can be used to shorten the time for preloading if the time is a major concern. Vertical drain are typically installed to a depth of 30 meters or more than 60 meters in some project. So that so it is important to carry out for the salt investigations, okay, prior to the use of the preloading and vertical drain methods. Okay? So what is the common soil investigations work? To get the information of the thickness of the soft soil layer. Okay. Usually the contract or the consultant we propose to use the cone penetration test CPT, okay, to get the informations on the soft soil. Okay, so preloading is effective when the loading is higher than the soil pre-consolidation stress. Okay, so what is soil pre-consolidation stress? Okay, so soil pre-consolidation stress, okay, or we call it as a PC or sigma C, okay, we may determine from what we call as from the odometer testing. Okay, so this PC is the is this uh, is used, okay, to determine what we call as the over consolidation ratio, okay, of the soil. Okay, so to increase the strength of the existing soil, okay, so we need to use a higher loads, okay, in order to make sure that the soil become over consolidate. Okay, so we need to carry out for the odometer test. Okay, then in order to make sure that the preloading is effective, the load that apply on the weak soil should be greater than the pre-consolidation stress obtained from the odometer test. Okay. So field preloading is more suitable if field material is inexpensive and readily available or a part of permanent structures such as embankment. Okay. So as I mentioned before, okay, uh, for the preloading, okay, usually it is a permanent load or structure. Okay. Then we have a surcharge, so we consider as an additional loads, and then later on we may remove from the preloading or from the embankment. Okay. So vacuum preloading is more suitable for the area where the soil are too weak to support construction equipment and field, or if field material is expensive and not readily available. Okay? So it's very far to transport or to export the actually to import the field material to be filled at the site. Okay, so then the use of the vacuum preloading is another alternative. Okay, okay. So when permeable layer exists close to the ground surface, okay, they may pose challenge for maintaining the vacuum preloading. Okay? Because usually the soft soil, okay, and the top of the soft soil, okay, or they call it a topsoil, okay, it's not, this is less permeable compared to the soft soil. Okay, so if we deal with a full soft soil, okay, so there will be a problem on the use of the vacuum preloading. Okay. Okay. So now we look on the advantages and limitations of the preloading process. Okay. So the advantages is reliable ground improvement methods. Okay. It has been used for several hundred years. Okay. And considered as a reliable ground improvement method and has a long track record of many successful case study. Okay. So it's often cost effective if fill material is readily available or a part of a permanent structure. Fill, fill preloading can be easily implemented in open land with limited or no demand specialty construction equipment, skilled worker, and quality control assurance. Yeah? So because we just lay on the soil, then make sure that we compact the preloading, okay, in stages. Okay. Usually when we use the preloading methods, okay, so usually the thickness, okay, uh, for each layer before we reach the desired heights, okay, we use around 300 millimeter thick. And after the compaction approach, okay, then let it settle on the ground for at least 1 week. Okay. Why? Because we need to let the excess pore water pressure value, okay, not too much exceeding the effective stress, or sorry, exceeding the pore water pressure at the ground. Okay. So let's say if we lay the one layer of soil, then later on we just continue to lay another one. Okay? So it may increase the excess pore water pressure. Okay? Then it may greater than the effective pore water pressure or pore water pressure itself. So then it can make the foundations, okay, to be weak, and later on it can collapse. Okay. So the thickness and the time allow, okay, is the most important things during the process of the preloading. Okay, we will discuss later on. Okay. So then the use of the vacuum preloading, okay, it will give a good advantage, okay, where no fill material required, short construction periods, and no need for heavy equipment. Okay, so that is the advantages of the vacuum preloading. Okay, okay. Now we look on the limitations, sorry, of the preloading methods. Okay, so the main limitation of the preloading is longer required time for consolidations. Okay, especially used for low permeable soil. Okay. When vertical drain are used, they require high headspace for installations. Okay? But when we deal at a large area, okay, and it's not a confined area, so there will be no issue on the use of the vertical drains. Okay. So there will be the method may not work well within constrained area because of material transportation and induced ground movements. Okay. So there will be a constraint, okay, if we have a very confined area, okay, and also the soil is too weak, okay, whereby to access the machines is very difficult, okay. Therefore, we need to treat first uh, the the soft soil, okay, to allow for the machines easily to enter to the sites. Okay. So the limitation of the vacuum preloading are the magnitude of the vacuum pressure limited by atmospheric pressure, okay, theoretically 100 kPa, and potential crack in the surrounding area due to inwards lateral soil movements. So the limitation of the vacuums preloading, it has a limited magnitudes of the vacuum pressure. Okay. As I mentioned before, if there is a limitations, so then there will be a combination between preloading, vacuum preloading, and the vertical drain methods. Okay. All right. So that is for the preloading methods. Okay. So let me try to find, okay, in the YouTube, okay, to explain on the preloading, vacuum preloading, and PVD or prefabricated vertical drains. Let me stop first this slide presentation. First, we look on this preloading methods. So there is no example on the preloading. Okay, we go first for the uh, prefabricated vertical drains, and there will be a combination of preloading. Okay. Okay. Okay, this is a very simple one. Okay. By Kellen. Okay, so this is the installation of the prefabricated vertical drain. So they install until it reach the hard area. Okay. So then with the use of the preloading, okay, so it uh, reduce the compressibility of the soft soil. Okay, so that is the example of the uh, prefabricated vertical drain plus with the preloading. So now we look on a different. Okay, this is a vacuum consolidation. Okay, they install first the prefabricated vertical drains. Then they lay all the geomembrane, okay, to make it the the area is tight. Okay, so then they apply a load on the top of the system. Okay, and then apply the vacuum, okay, to allow for the water, excess for water pressure to dissipate. Okay. So we look on this. Okay, some of the terms they use a weak drain, vertical weak drain, or they are called also a weak sand. Okay, they are use of the sand. Okay, to create as a vertical uh, drain system. So this is a pre-navigated vertical drain. Sorry. Okay, this is the combination of preloading and PVD. Okay. Okay, we look on the last one. Okay, this is called as a Sandler method. Okay, so this is the implement and the compressor. Horizontal drain. Okay, this is a vacuum preloading. So there is some example on the PVD preloading. So, okay, and also why they come up with the PVD, okay, due to the limitations of uh, or depletion of the what we call as the sand. Okay, so then they come up with the use of the geotextile to make or construct for the vertical drains. Okay, so then we continue for the next remaining slide. Okay. So then we have discussed on the concept of the preloading. Okay, so now we look on the principle of the preloading. Okay. So we have here the pre-compressions, okay, stress and ground movements, consolidation theory, and field combined preloading and surcharge preloading. Okay. Okay, so this is an example of the explanations, okay, between the void ratio and effective consolidation stress. Okay. Later on, this next okay. Okay. So then the shear, once we have increased, and once we have decreased the void ratio, so simultaneously it increased the shear strength of the material. Okay. So when the consolidation stress on the soil elements increase from the initial overburden stress, okay, so this is the initial stress at the site, okay, which is point A. Okay. So then we have applied the preloading loads. Okay. So we have applied the preloading loads, okay, which is a delta sigma z. Okay. So then from A, okay, we move to B. Okay. So the void ratio of the soil decreased from E0 to E1, okay, following the compression line. Okay. So that is very common when we apply a surcharge or additional loads. So then there will be decreasing of void ratio. Okay. So after the completion of the consolidations, okay, the applied stress is removed. Thus, the consolidation decreased to sigma z naught. Okay. So once we have we apply the preloading, so then we remove, okay, the surcharge. Okay. So then the consolidation stress will decrease, okay, to the sigma z naught. Okay. So during the process, the rebound to the dash line, okay, from B to C, okay, so then it has a new, what we call as void ratio value, okay. So it is clear that the E naught or E naught prime is less than the E naught, okay. So what we can understand, okay, the soil densified, okay, because the void ratio has been reduced, although we have removed the surcharge. Okay, so that is the concept or principle of the preloading. Okay, when we apply a surcharge, and when this is at the actual effective vertical stress. Okay, so then we apply a surcharge. Okay, then we remove the surcharge. Okay, so the difference between A and C is considered as the densified of the soil is happens. Okay. Okay. The basic principle of preloading is to reduce the bulk ratio of soil by consolidation, thus reducing the compressibility and increase the strength of the soil. Okay. So the first graph to show that the reducing of the soil compressibility. Okay. Next graph to show that the increasing the soil strength, okay, similar like what I have discussed before, okay, from A, okay, they increase the effective consolidation stress until it reach the B, okay, then they remove what we call as the surcharge, then it will rebound again to the C. Okay, so what we can learn here, okay, from A to B is the process of uh, consolidation of preloading. Okay, once the preloading is removed, okay, the strength will be not rebound to the actual conditions, but it may rebound at C, means that the shear strength has been increased a little bit, okay, due to the process of the preloading and removal of the preloading. Okay, so that is the concept, okay, the first concept of the preloading process. Okay. So if a permanent structure is constructed afterwards, okay, the stress increase from C to B, okay, and the load that we apply is less than the, or the load that we want to construct, propose to construct, should be less than the first stage where we apply the preloading. Okay? So the induced void ratio reductions, which is the delta E, following the recompression time is much smaller than that induced by the A to E. Okay? So it is less. Means that the A E is less than the delta E. Okay, sorry, delta E from the new proposed loading, okay, is less than the delta E during the preloading process. Okay, means that although apply a new, okay, then what we have I do the preloading stage. Okay, need to understand, okay, how much load can need to propose. Okay, okay, less than because the bidding process. Okay. Okay, this is for the and ground movements. Okay, so this is a stress path. Okay, So there is a K knot line. This K knot line represent what we call as a deformations not happen because it is at rest. Okay? So above the K line, okay, so it is considered as an active area. Okay, so there will be a movements in lateral. Okay, still there will be a movement from the vertical. Okay, but the movement in lateral is happens. Okay, so we need to make sure that it doesn't reach this failure line. Okay. So it is shown that the field preloading result in an stress path AB, okay, so this is A and B, towards the failure envelope. So this is the failure envelope, KF. Okay. There is a possibility of failure during the field preloading. So salt consolidation during a waiting periods follow the stress path of BC. Okay. So means that we need to understand, okay, what is this failure line and make sure that it doesn't cross the failure line. Okay. So after we feed the placement, then allow for the consolidations happen, okay, based on the BC lines. Okay. However, vacuum preloading result in horizontal path AE, which move away from the failure envelope. Therefore, no failure is possible during the vacuum preloading process. Okay, so that is the advantage on the use of the preloading process. Okay. So the stress path AD represent a K knot consolidations, okay, where there is no horizontal deformations happens at this K knot line. Okay, means that during the consolidation, during the preloading process, okay, definitely there will be vertical movement and also outward horizontal movements happen at the side. Okay. However, for the vacuum preloading, there will be a vertical movement happen. Okay. At the same time, there will be a inward horizontal movement happens. Okay. So there is no outwards horizontal movement happen. Okay. So for this area is considered as a passive area. Okay. So this figure also represent the triaxial conditions for point A. This is point A. Okay. So this is the K naught, which is at rest, times with the sigma 1, which is the vertical effective stress. Okay. B, okay, C, okay, B to C, okay, there will be an additional surcharge occur take place when we apply for the preloading. Okay, so then at D here, okay, so the additional surcharge, okay, will add, okay, on the what we call on the vertical, sorry, on the horizontal on the lateral force on this sample, okay, while E, okay, so the delta sigma z, okay, does not be multiplied with the K naught. Okay, so means that the increment of the lateral stress is less as compared to the D. Okay. So field preloading and vacuum preloading have three obvious differences. Okay. The field preloading induce positive excess pore water pressure in geometrium, while vacuum preloading induce negative excess pore water pressure because we use the vacuums. Field preloading induce unequal vertical and horizontal stress, while vacuum preloading induce the same vacuum pressure in all directions. Okay, so this is has been shown in this diagram of DC, while this is on E. Okay. Field preloading induce upward movements in the horizontal directions, while vacuum preloading induce inward movements. Okay, has been shown here. Okay. Okay, so this is what has been discussed in the here in the slide. Okay. Okay. So then stress and ground movement. So field preloading induce outward horizontal, while vacuum preloading induce inward horizontal. Okay. So both has show a vertical settlement happen. Okay. However, for the embankment of preloading, it induce outward horizontal. Okay, while for the vacuum, it induce an inward horizontal movements. Okay. 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 So this is to show you what happens, okay, in terms of the pore water pressure, okay, and the effective stress profile under field and vacuum preloading. Okay. So during the field preloading, we apply a load. Okay. So then it increase, okay, the the excess pore water pressure. Okay. Once we have increased the surcharge on the top of the okay. So it is shown that at the moment of field loading, okay, the initial hydrostatic water pressure, okay, is increased, okay, by the amount of additional field stress. Okay. And the pore water pressure, okay, decrease with time. Okay. This is the excess pore water pressure. Okay. Will decrease, okay, with times, okay, or the remaining positive excess pore water pressure, okay, will decrease with time, okay, at the bottom depth. Okay. As a result, the effective stress in geomaterial, okay, increase from initial overburden stress, okay, from the initial, okay, yes, the effective stress in geometry increase with the initial vertical overburden stress at time of T. Okay, on the other hand, at the moment of vacuum preloading, okay, the initial hydrostatic water pressure is reduced by the amount of the vacuum pressure. Okay, so this is during the suctions, which is negative atmospheric pressure. Okay, and the pore water pressure increase, okay, with time. At the time of T, okay, the remaining negative pore water pressure. As a result, the effective stress in soil increase, okay, from the top of the sigma z, okay, to the sigma z plus us, then minus with the excess pore water pressure. Okay, so if the vacuum pressure and additional field stress are equal, and positive and negative excess pore water pressure dissipate at the same time, the effective stress increase by field and vacuum loading are equal, okay, at the last depth of Z. Okay, so that is the concept of the pore water pressure change and effective stress change between the field preloading and vacuum preloading. So for the vacuum preloading, okay, we reduce the atmospheric pressure, okay, while for the field preloading, we increase we apply the surcharge, okay, and it, what we call as increase the pore water pressure, okay, due to this applied surcharge. Okay. Okay. The last one is the use of the vertical drains. Okay. So to accelerate the conservation of the soft soil, vertical drain can be installed in the soft soil to provide another and short drainage path. Okay. So later on we will discuss, okay, in consolidation theory, okay. So we have CV for the vertical movements, okay, and we also have a CR, okay, where the use of this vertical drain, okay, can help to increase the CR value, okay. So how to get the CR and CV? It depends on the KV and KR. Okay. However, in the vertical drains, during the installation process, okay, there will be an effect of smear. Okay. So we may consider it during the operations for the vertical drains. Okay. So to accelerate the conservation of soil, vertical drain can be installed in soft soil to provide another and short drainage path. Okay. So this is to show that how the vertical drain works. Okay. The unit cell has a drainage surface on the top and bottom. Therefore, the longest drainage distance in the vertical drain is HDR. Okay. Due to the inclusion of vertical drain, water can also flow radially down towards the drain. After the water reaches the drain, it will flow vertically inside the drain to the top of the surface. Okay, because the diameter of the vertical drain is relatively small compared to the vertical or the length of the drain. So means that horizontal or radial movement will be happen first, then we continue with the vertical movements inside the vertical drains. Okay, so with the use of the vertical drain, there will be a combination between CV and CR. Without using the vertical drain, we only have the CV. Okay. Okay, so we take a rest for 15 minutes before we go for this slide. But before that, can we take a photo? We miss I-50.